This is the outline of my talk. So first, I will give an introduction about the vorticity and the magnetic field in heavy-ion collisions. Then I will first focus on the CME search in heavy-ion collisions, and also what would be the important theoretical approach to understand the CME in heavy-ion collisions. In that aspect, we need to understand the realistic evolution of the magnetic field. Then I will turn to a new subject, that is the deep learning assisted CME search. After that, I will go into the subject of spin polarization of hyperons and the spin alignment of vector mesons. And finally, I will summarize. So let's begin with the B field and vorticity in heavy-ion collisions. If we consider a non-central heavy-ion collision, it's very easy to understand that there is a angular momentum of the gliding system, and it's not difficult to estimate the strength of the angular momentum, which is given by the average distance times the average momentum. And for the gold-gold collision, you can estimate that this angular momentum is about 10 to the 6 times the h bar, if the centrality is given by the impact parameter of 10 Fermi. And because the nuclei are charged, when they move, they generate this magnetic field. And in this gliding case, at 200 GeV of gold-gold collision, you can estimate the strength of the B field and found that it could be very large. It could be 10 to the 18 Gauss. So this rough estimation, and if you do some numerical simulation using some quite commonly used realistic models of the heavy-ion collision, like Ising model, you can actually nicely calculate the magnetic field. So here I show you the calculation from our simulation, which I did with Wei Tian Deng some years ago. And you can see that indeed in the heavy-ion collision, there is a very big magnetic field which increases with the centrality. Here I show you the energy dependence of this magnetic field, and you can see that roughly it is a linear function of the colliding energy, square root of S. In fact, this magnetic field is very strong, and is the strongest magnetic field that we know in the current universe. But it's very transient, which means it decays very fast. However, we know that in heavy-ion collisions, we have a conducting medium, that is a quark-gluon plasma. And in that case, the magnetic field can be kept for a longer time. So that's the question. What is the realistic time evolution of the magnetic field in the heavy-ion collision? And I will come back to this point later. So here is a comparison of the strength of the magnetic field. So basically, in heavy-ion collision, we generate a very, very strong magnetic field. In fact, the similar calculation was done by many, many groups. So I just list a few of them here. So this is the initial magnetic field. Similarly, the vorticity can also be calculated by using some transport models. For example, the EMPT model. Here I show you the calculation given by Yin Jiang, the Ziwei Lin, and Junfeng Liao. You can see that as time goes, the vorticity drops because the system is expanding. Here I show you the energy dependence of this vorticity averaged over the overlapping region of the generated medium and also average over many events. Very interestingly, you can see that when the colliding energy is small, this vorticity roughly go with the energy, simply because if you have a higher energy, you have a higher colliding total angular momentum, so the vorticity could be larger. However, when the energy goes to very large, namely if it is larger than like about 10 GeV, then the vorticity actually drops if the colliding energy increases. This is a relativistic effect, which now I understand that this is due to the fact that at higher colliding energy, we could have a better Bose invariance in the medium at mid centrality. Because what I show here is actually the vorticity at mid rapidity. But this monotonic behavior of the vorticity as a function of the square root of s is very interesting. I will also come back to this feature later. So another important information from the calculation is that the vorticity itself is actually very large. Its magnitude can be about 10 to the 21 per second. And this, compared to any other fluid that we have ever known in nature, this actually is the most vertical fluid. What we have is the most vertical fluid in the heavy collisions. So again, I need to stress that there were many similar calculations in the literature, and basically all those calculations gave important agreement that we have a very strong vertical fluid in the heavy collision. For the vorticity, there is another very interesting source. In the above, what I talked about is the vorticity induced by global angular momentum. However, in the heavy collisions, after the collision, the system, the fireball will expand. And it expands in inhomogeneous and in an inhomogeneous way. And this case, this inhomogeneous expansion will also generate a type of vorticity. And in this case, as I show in this cartoon, this vorticity would be like a smoke ring in finite rapidity. And the numerical simulation indeed show that at finite rapidity, here you see that at rapidity plus and minus 1, there is this ring type vorticity. This simulation was done by Xuguang Huang and Qun. Well, this is due to the longitudinal expansion. Also, we have the transverse expansion, and if we have a non-central collision, this transverse expansion is anisotropic. That's why we have the V2. And in this case, there is also a vorticity pointing along the beam direction. That's the longitudinal vorticity, which in the transverse plane of X and Y form a quadrupole pattern. Here I show you the thermal vorticity, but for the usual kinematic vorticity, it has a similar quadrupole structure. And again, I need to say that there are other calculations which give the similar result. Okay, so now we see we have strong magnetic field and vorticity in the heavy collision. What would be their effects? So one of their effects is that both the magnetic field and the vorticity can polarize spin. So suppose we have a spin fixed in space, and under the magnetic field and the vorticity or rotation, because there is this magnetic moment and the magnetic field coupling, and also the spin and the rotation coupling, we see that both the magnetic field and the rotation could polarize the spin of this particle. Now, if we let the particle move, for example, if we consider a movable charged fermion in the magnetic field, in this case, in addition to the spin polarization given by this simple Hamiltonian, there is also the Landau quantization of the orbital motion. And we will have the Landau levels. And the lowest Landau level is quite special because here I consider the massless fermions, because in this case, you will have two branches of the dispersion relation, one corresponding to the right-hand fermion and another corresponding to the left-hand fermion. And this lowest Landau level case, the special thing is that the spin is fully polarized. In this case, for example, here the cartoon shows that the spin is polarized upward, namely along the magnetic field. And in this case, the right-hand fermion will move along the magnetic field because by right-hand fermion, its momentum is parallel to its spin direction. And for the left-hand fermion, its momentum is opposite to its spin direction. So, which means if we have more right-handed fermion than left-handed fermion, there will be a net current along the magnetic field. This is actually the Carroll magnetic effect. More careful calculation can show that this effect gives you a vector current proportional to the applied B field, and also how much is the balance between the right hand and the left hand fermions. So, okay, though in the following, let's focus on the Carroll magnetic effect. So in the heavy collisions, why the Carroll magnetic effect is, of course, the Carroll magnetic effect itself is very interesting, and is a very universal phenomena, which can also appear in other physical systems, even in condensed matter system, and was also a hot topic in condensed matter physics. But in our field, this is particularly important because it could be used to probe the QCD topologic sector. So here I show you a cartoon to explain the main idea. Theoretically, the QCD permit parity violating phases or parity violating configurations. For example, let's say if there is an initial topological fluctuation which could induce some parity violating domains, and then through the QCD Carroll anomaly, those domains could generate some Carroll imbalance of quarks through the triangle diagram. Well, and then through the QED Carroll anomaly, the B field or the rotation could generate the vector current through the Carroll magnetic or Carroll vortical effect. I didn't explain the Carroll vortical effect, which is a similar effect as the Carroll magnetic effect. And if this happens, because the B field and the omega is roughly along the direction perpendicular to the reaction plan, so this will generate a charge or baryon number separation with respect to the reaction plan, and which could be possibly observed by design some suitable observable like the gamma correlator. And indeed, there were the measurement by star collaboration for both the charge separation and the baryon number separation. However, we know that, for example, for the Carroll magnetic effect, the signal itself is quite small, and there is a big background due to the elliptic flow. And here is the result given by Jie Zhao in Quark Matter 2019. You can see from the current experimental data, the signal itself could be small. More importantly, because the signal of CME would be proportional to the magnetic field, and the background, the V2 itself also in some sense proportional to the B field, because both B field and V2 are increasing if you increase the centrality. So which means the signal and the B field would have similar geometry dependence. So this make it difficult to disentangle the signal from the background. And the nice idea recently the experimentalists had is to use the isobar collisions. In this case, they would collide the zirconium and ruthenium system separately. And in this case, in these two colliding systems, the geometry is roughly the same. So namely, these two nuclei have similar atomic number, but they have different charge number. So they would generate a different magnetic field. So in this way, the background can be fixed, but the signal itself, which is expected to be proportional to the B field, would be different. And indeed, the theoretical calculation shows that there is a relative difference between these two colliding systems of the magnetic field. Here I show you the magnetic field is squared projected to the direction perpendicular to the reaction plane. And you can see that the relative difference between these two systems for the magnetic field square is about 10 to 20% difference. Well, for the centrality and centricity difference or V2 difference could be very small if we focus on the centrality region of 20 to 60%. So from this information, we can extract the relative difference of the CME signal by using a two-component model of the signal and the background. And the result shows that if the background level is 67%, and if we have 400 million euans, this isobar collision could give us 5 sigma significance to tell whether there is a CME. And in 2018, the rig first run of isobar produces 3 billion yuans. In this case, so even if the background level is as higher as 88%, we still could tell whether there is a CME at a significance of 5 sigma. And even if the background level is like 93%, we still can see whether there is a signal at 3 sigma significance. So which means the isobar collision is quite promising, and so we are very looking forward to the results of the isobar experiment. From the theoretical point of view, we need to quantify how the CME is generated in the heavy-ion collision and how this CME is finally transferred into the observables. So we need to quantify the CME in theory. In this case, we basically have 2 available theoretical tools. First is the hydrodynamics, and another is the transfer models. For the hydrodynamics, and the reason there was the AVFD model, which can be used to couple the evolution of the actual charge and the bank medium evolution, and finally transfer the actual charge and to the observed signal. Another way is using the transfer model, like the EMPT model. Recently, this was performed by several groups, like, for example, the Guliang's group. And also we did some simulation. But in all those theoretical models, there are two theoretical uncertainties which are so far unknown. The first one is how much the initial actual charge is, and the second one is how the B field involved in the in the system. For the first situation, so far there were no solid calculation, because this is a non-perturbative process. But in another sense, this is actually what we want to know from the data, because we want to know whether there is an initial actual charge, or which will indicate whether there is an initial topological fluctuation. But anyway, this is one big uncertainty for the theoretical calculation of the CME evolution in the Hadron collision. Another big uncertainty is the realistic evolution of the B field. So far, most of the calculation of the B field is for the case of a vacuum motion of the charges. So namely, the magnetic field is induced by the moving spectators, and then when the spectator leave the colliding region, the magnetic field will drop. However, in the realistic case, there would be the hot medium of quarks and gluons, and this medium is conducting. And so when the B field drops, it will generate a Faraday current, which will try to capture the B field, and this way the B field actually can be kept much longer if the conductivity is larger. So here is the so here is the case of a vacuum. So if the medium is insulating, and in this case the B field drops very quick, and which can be well fitted by using this similar formula. Here I show you that this formula is very well fitted to the numerical data. And in this case, the B field lifetime is very short. And recently there was some theoretical calculation by using hydrodynamics. In those calculations, as you can see, for example, this ICO QGB calculation given by Injirami and his collaborators. You can see if you consider the conducting medium, the B field can indeed be kept much longer than that in the vacuum case. And there were also the calculation by using other hydro code, and recently there is also a calculation by using EVFD, and show that indeed when the conductivity is encoded into the hydrodynamic evolution, the B field could be much longer lived. However, we know that in the realistic case, the hydrodynamic evolution can only happen after the system is locally thermalized. Before that, the B field could be possibly already decayed a lot. Or in other words, we also need to understand what is the B field involves in the pre-hydro region. And in this aspect, we recently made a simulation by using a coupled set of equations of a Maxwell equation and Boltzmann equation. So we solved the Boltzmann equation and the Maxwell equation together by using with the initial condition for the electromagnetic field given by the moving colliding nuclei case. Okay, and for the initial condition for the quark and the gluon distribution, we use the CGC in spirit distribution. So here is the, and in this calculation, we consider a 2-to-2 process between quarks and the gluons. Here I show you the T channel, and there is also the S and the U channel for those collisions. So the, okay, so here is the simulation of the longitudinal pressure and the transfer pressure. We also consider Bjorken expansion. And in this case, you see that although the system evolves towards the equilibrium, but it could be quite slow, which means we need to understand how the B field evolved in out of equilibrium media. Here is the result. In the case of a Bjorken longitudinal expansion, our result shows that when we have the medium, the B field decay is much delayed. However, it's still much smaller than that obtained by hydrodynamics if you assume that the hydrodynamics can start from the very beginning. So our result can be used for the further study of the magnetohydro evolution of the magnetic field. So which means, for example, IQQSP could use our result as input and to run the hydro code further to see how the B field is involved after this kinetic region. Here I show you the longitudinal distribution of the B field. As you can see, when the spectators moves longer, the B field becomes the B field in the colliding region becomes different from that in the vacuum case due to the Faraday effect. So here I show you the induced Faraday current due to the decay of the B field. So when this two spectator leaves the colliding region, the B field will drop, and then there will be a Faraday effect induce this two current. And if we now calculate the ratio between this current and the induced, and the electric field, we will obtain an effective conductivity. So which characterize the capability of the medium conducting the current in an out of equilibrium system. So as you can see, in the late time, the conductivity, the effective conductivity could become very, very large. So indeed, we will have a nice conducting medium due to the production of the quarks. So if we, in the initial stage, already put some quarks, then in addition to this Faraday current, we would have strong Hall current. Although in this case, we could also have this Hall current, but the Hall current is smaller than the Faraday current. So we will have a positive conductivity. But if we have much more charge carrier in the system, the Hall current could be stronger than the Faraday current. And in this case, near the colliding center, we would have a negative effective conductivity. So this means the direction of the current near the mid-rapidity region could depends on how much quarks are produced. And this means this direction could it depends on the colliding energy. So this could have some implication in the Huang collisions. Cool. Okay, so let me turn to another topic. It's about the CME search using the deep learning assistance. So let me recall that the main challenge of the CME search is that we need to find a way to disentangle the signal from the elliptic flow driven background, and which is very difficult. Because all those designed or observables are based on the final hadron distribution in the momentum space, then why don't we just look at the distribution itself of the charged hadrons? And in this case, we can think the following situation. So we have this events. Whether there is a CME, could result different charged hadron distributions. And this would be similar to the situation that we want to distinguish between a cat and a dog by just looking their faces. So whether we can distinguish whether there is a CME in that event by just looking at the charged particle distribution in the momentum space. If there is a CME, that's the 1, and otherwise it's the 0. So this is a very similar to the cat-dog problem, and which is already known that could be very well done by using the machine learning method. So then we train a machine to recognize the initial charge separation, which will mimic the CME. We use the convolutional neural network, which was already proven to be good at the pattern recognizing of the faces. So in this situation, we produce the momentum distribution of charged pions by using EMPT with and without the initial charge separation. And this will generate two sets of images in the momentum space, in a two-dimensional momentum space. Then this image will be input into our CNN convolutional neural network. And after this situation, in the case there is a charge separation, we will teach the machine that this is the case of this is the case to be labeled by 1. Otherwise, it is labeled by 0. So after this training, the machine will learn that whether an image is produced from the event with or without initial charge separation. And then we use the machine to do the test. So for each centrality and each colliding energy, we generate 50,000 events for the training. And after the training, we test the machine using randomly produced events. So here I show you the result. As you can see that the machine can indeed learn some key feature of the charge separation. So it can very well recognize whether there is an initial charge separation or not. And this learning is independent, I'll say, almost independent of the centrality and the colliding energy. For the dependence of the charge separation rate, if we train the machine with the training set of 5% or 10% initial charge separation, and then for the test event of charge separation more than, say, let's say 10%, the machine can always tell that, okay, there is or there isn't a charge separation with a very high accuracy. And for the case of a lower initial charge separation, the machine can still behave quite well. So the machine is very robust. It really learns some key features of the charge separation. Then we made then we compared the machine to the usually use the gamma correlator. So here this part is the gamma correlator, and from the gamma correlator we define a relative difference for the situation with or without the initial charge separation. So this quantity R gamma would quantify the sensitivity of the gamma correlator to the initial charge separation. And we make a comparison between this R gamma and our machine. And for the, yeah, so as you can see that the machine behave much better than this gamma correlator in this 10% test set. Okay, as we know that the elliptic flow can give a big background to the gamma correlator. Then we test whether the machine learned whether the machine whether in the case using machine learning, the result depends on the V2. So here is the result. This P1 is the test accuracy. You can see that in the case of a small V2, there is a dependence of the accuracy of the machine. But when the V2 is larger, the machine behaves independently of the V2. So which means the machine learns something which is not the elliptic flow driven background, but the essential feature of the charge separation. Okay, so this is very interesting. But in the future, we need to understand, of course, first we need to optimize the machine. And also we need to understand why the machine can do the, or why the machine can work so well. And we also want to apply, if possible, to the real data and also to the, for example, the isobar situation. Although we have some result, but in the current statistics, the error bar is quite large. And also we could train a machine to learn the features of a ferromagnetic wave and so on. Okay, so let's turn to the spin polarization of hyperons. So the early idea of spin polarization of hyperon was given by Xuguang Liang and Xuguang Huang 50 years ago, and also by Woloshin. And the idea later was interpreted by a picture of vorticity using this vorticity spin coupling. And due to this coupling, if there is a vorticity, there would be a spin polarization. And later, Francesco and later other people derive a more rigorous formula to connect the spin polarization with the thermal vorticity. So here is the definition of the thermal vorticity. So I should emphasize that this formula was derived by assuming a global equilibrium, although recently there were arguments that the similar could be applied also to the case of a local equilibrium. But anyway, this formula could apply only when the system is close to equilibrium. This similar formula is a kind of a spin Cooper-Frye formula. So which means this, if you obtain the thermal vorticity, you can use this formula to obtain the polarization, okay, through the phase out. Here is the result. For the global polarization of a lambda hyperon, the experiment and the theory match quite well. And also the calculation of the polarization as a function of centrality can also fit the data quite well. This calculation was done by Chi, Kai, and our organizer, Hui Chao, and myself. So in this sense, here I show you many different calculations from different groups, but the message is that the vorticity interpretation of the global lambda polarization works quite well. So, and last year, the Hedis reported a measurement of lambda polarization at 2.4 GeV, which is, although the error bar is large, close to 0. This is comparing to the, as I showed you in the beginning of the talk, the vorticity depending on the cladding energy. So you'll see that this could be possibly matched to each other. Of course, there are some missing energy region from the data, but it's quite interesting. And also we need to study, which means we need to study the polarization at very low energy, and this would be covered by Nika, Fair, and FIAF, and also be SCAN2 at RIC. To calculate the polarization at this low energy from theory, we really need some out of equilibrium theoretical tool, and so far we don't have such tool. But in any case, we could expect that the polarization of hyperon in this region should be proportional to the angular momentum in the guiding system. And recently, STAR collaboration reported the measurement of the global cascade and omega polarization through the measurement of the lambda particles. Even in this case, we can see that the theoretical calculation and the data could fit within the error bar. If we consider all those theoretical calculations didn't consider the fade-down effect, but we can estimate how strong the fade-down effect could be. For the cascade case, the main decay channel is this one, the decay from the cascade 1530 to cascade minus and pi. In this case, from our study last year by Xuguang Huang, Huanzhong, and myself, in this case, this decay channel could contribute about 40% of the cascade minus yield and about 30% of the cascade polarization. And this contribution is positive, which means if we consider this fade-down contribution, the theoretical curve of a cascade would slightly lift up. But for omega, there is a very small, the fade-down contribution is very small. So in this case, we can still see that the vorticity interpretation of the global, the cascade and omega polarization still works. This is the global polarization. Let's consider differential lambda spin polarization. That's the polarization as a function of kinematic variables like the PT, rapidity, and azimuthal angle phi. For the PT and rapidity, our recent calculation using music hydro shows that the numerical result could fit the data within the error bar for the case of 27 GeV, and a little bit lower than the data for the case of 200 GeV. But if we go even higher rapidity, then the situation is quite uncertain, because even from the theory, the different theoretical model gives a different rapidity dependence of the vorticity or the polarization. So I think it could be interesting to look at the large rapidity region from both the theory and the experiments. The situation for the azimuthal angle phi dependence is even worse. So in the longitudinal polarization, Francesco and Carbonco made some theoretical calculation, which found that if we decompose the phi dependence into different harmonics, the second harmonic flow F would be negative from the theoretical calculation. However, the star data 2 years ago shows that this harmonic coefficient is positive. Similarly, for the transverse polarization, the theory gives that the second order harmonic G should be negative, while the data still gives a positive value. So this is the sum problem for the spin polarization. Then how can we understand this sum problem of a lambda spin, a local lambda spin or differential lambda spin polarization? For this purpose, first we need to understand the vorticity. And for the vorticity, I think we understand it very well. And the lambda polarization contains a bigger fraction from the fade down decays of higher lying hyperons. We also need to understand the decay, fade down decay contribution to the polarization. And this was done last year by 2 groups, one from the Baccattini and one from our group. And the result shows that the measured lambda polarization, although contains a contribution from fade down decay, but it cannot be explain the puzzle of local lambda polarization. Another way from the theory to understand the local lambda polarization is to go beyond the equilibrium treatment of the spin degree of freedom. And recently there were works in this direction in both hydrodynamic framework and kinetic framework. And also there are some other recent efforts to understand the local lambda polarization. But so far, I would say that this spin sum problem still unsolved. However, it inspires many theoretical developments about the spin dynamics, both in and out of equilibrium. Okay, so let me turn to the discussion of the phi spin or vector Meson spin alignment. Because it can polarize spin, so it can polarize any spinful particle, whether fermions or bosons. For example, the vector Meson could be polarized by vorticity. So if we consider vector Meson from the quark recombination, in this case, if we know the quark density matrix, we could easily obtain the vector Meson spin density matrix. And in this case, if you look at the 0,0 component of this spin density matrix of vector Meson, you can find that it is given by this formula. If the quark and anti-quarks are polarized in the same magnitude and direction. This formula was first obtained by Xuguang Liang and Xuguang Huang. And this formula shows that this rho 0,0 quantity should be always smaller than 1/3 and only slightly smaller than 1/3, because we already know that the polarization or the vorticity contribution to the quark polarization should be very small. However, last year, both Star collaboration and Alice collaboration reported the experimental result of the vector Meson spin alignment on the rho 0,0 of phi and k star 0 mesons. The result gives puzzles. The first puzzle is that for the most centrality, you can see that the rho 0,0 is far from 1/3. It's almost 2 orders bigger than the expectation from the vorticity in both the Star case and also the Alice case. So this is one big puzzle we don't understand. And recently there was a proposal by Sheng, Oliver, and Chun Wang assume that in the non-central colliding case, there would be a Masonic strangeness field, and the spin could also be polarized due to this field. In this case, they could qualitatively explain this rho 0, 0. This is the puzzle one. Another puzzle is that if you there's a big error bar for the iris in the central case. So let's focus on the star data at the central collision. You can see that the rho 0, 0 is though the error bar is still large, but for in this case and this, you can see that the rho 0 is smaller than 1/3 in the central collision. Although we know that in central collision, the average vorticity or other field like magnetic field should be 0, but the vector meson is still be polarized. Okay, then how to understand this vector meson polarization or vector meson spin alignment in central collision? So remember that in the inhomogeneous expanding case, there will generate the ring type vorticity in the direction in the forward rapidity and the backward rapidity region. Okay, so in this situation, if you rederive the rho 0, 0, you will find that the rho 0, 0 could receive contribution not only from the py, that is the polarization of quarks along the global angular momentum direction, but also from the px and the pz. So in this situation, if the quarks, let's consider central collision, if the quarks are polarized due to this ring type vorticity, so we can model its polarization in this way, and then you can find that the rho 0, 0 of vector meson is given by this formula. And if you make an average over the azimuthal angle, you can see, you can find that the average, the rho 0 is indeed smaller than 1/3. So this was done. This calculation was done by Xuguang Huang, Huan Zhong, and myself recently. And this is the local phi spin alignment scenario. And this scenario can naturally explain why in the data for the central collision there is a there is a rho 0 smaller than 1/3. And to test whether this is true in experiment, we need to measure the rho 0, 0 as a function of the azimuthal angle. And I really look forward to, or I really hope that the experimentalist could look at this quantity as a function of the azimuthal angle. Okay, let me skip this. Okay, let me summarize. So we see that there are very interesting physics for the chirality, vorticity, and magnetic field and spin polarization. So we studied the pre-hydral evolution of the B field and see the Faraday effect and also the Hall effect, which would be change the B field evolution compared to the vacuum case. And also we developed a neural network to assist the CME search in the Hadron collision. So for the global polarization of hyperons, now we found that the theoretical calculation could fit the data quite well. Which means that the global polarization is quite possibly due to the global angular momentum. But for the local case, still is a puzzle. And for the vector meson spin alignment, there are also puzzles, but at least in the central collisions, the local spin alignment could possibly explain the data. Okay, thank you very much.